So as you can see, I have already written the degree of reaction as I was telling you. So there is another way of expressing the degree of reaction for the axial compressors, that is the ratio of the components of energy that is transferred due to the change in pressure of the fluid between the inlet and the outlet of the rotor to the total energy transferred is known as the degree of reaction. So what we basically mean is that how much of change in pressure is happening between the inlet and the outlet of the rotor upon how much total energy change we are getting from that stage. By that stage, I mean, as you can see here, by that stage, I mean the stator and the rotor as one complete stage. So that is we refer to as the degree of reaction. Now, as the degree of reaction is, already I have written the formula and everything, as you can see here. As you can see here, that is Rd equals to Cr1 square minus Cr2 square upon 2 Cbl multiplied by Cw2 minus Cw1. Now, previously I have shown you guys that the relations of Cw2 and Cw1 and Cr1 and Cr2 along with Cbl from the velocity triangles, we can derive the reaction, different, you can say formulas or different expressions for it. So we are just going to do that right now. And we can write, if you have any confusion, you can always go to the start of the video, and while you are learning, you can also draw the velocity triangle as I have drawn here. The velocity triangle for inlet and velocity triangle for inlet and the velocity triangle for outlet. Now, referring to the velocity triangle for inlet and outlet, we can write Cw2 should be equals to Cbl minus Cf tan beta 2. We have one of these relation, and the other relation we can state as Cw1 should be equals to Cbl minus Cf tan beta 1. We have this following relations, and we can just input this relation into the degree of reaction. But before that, we'll just simplify it a bit further. Therefore, Cw2 minus Cw1 should be equals to Cf multiplied by tan beta 1 minus tan beta 2. Let us state this equation as we have done the equation 8 in the previous equation, that is the isentropic pressure drop. So that is equation 8. We'll term it as equation 9 here. Now, from here, similarly from all the velocity triangles that we have drawn, you can see this expressions. That is, I'm writing Cr1 square should be equals to Cf square plus Cf tan beta 1 whole square. Similarly, Cr2 square is equals to Cf square plus Cf tan beta 2 square. These are simple relations from the Pythagoras theorem that we can derive by following the velocity triangles. So here also, I'll take the liberty and deduce this expression, that is Cr1 whole square minus Cr2 whole square. I'll just write it. And from this relation, we get something like this. Tan square beta 1 minus tan square beta 2. We get this relation, so we have all the terms we need from the degree of reaction formula, that is CR1 square minus CR2 square and CW2 minus CW1. And we have already derived this here in details by following the velocity triangle. So I'm just going to substitute this equation and this equation into the degree of reaction formula, and we get something like this: CF square tan square beta 1 minus tan square beta 2 by 2 CBL multiplied by CF tan beta 1 minus tan beta 2. You can keep it, you guys can keep this formula to this itself only, or you can derive it further. So let us mark this equation as 10, and you can derive it a even bit further, and we can write degree of reaction is equals to 1 by 2 CF by CBL tan beta 1 plus tan beta 2. This is our equation 10. Similarly as the earlier stage, it's just a simple crisscrossing of the excess terms that we get. So we are just going to keep it with equation 10 itself only here. Now, we have gotten the degree of reaction. What we need to do right now would be the efficiency of the stages. Suppose we are taking, we are taking in multiple number of stages and everything. So we need to know the efficiency of each of the stages. But before that, let's just discuss a little bit of degree of reaction. Degree of reaction for all practical compressors, axial compressors, or centrifugal compressors, it is kept as usually kept as 0.5, you can say. So if you just substitute RD equals to 0.5, you get a simplified relation in terms of CBL and CF and tan beta 1 and tan beta 2, a simplified relation. From this, you can also say that alpha 1 is equals to beta 2 and alpha 2 is equals to beta 1. That is a, you guys can do it as an exercise. Just put 0.5 for RD and you get a relation in terms of these, and further derive it with the help of velocity triangles. You will be able to find alpha 1 is equals to beta 2 and alpha 2 is equals to beta 1. This is just for a particular degree of reaction value, that is 0.5. Now, we'll be moving into polytropic efficiency, that is this is the polytropic efficiency. So what do we mean by that? Polytropic efficiency, we basically will be moving through a polytropic process for us for an axial compressor, and we will write down the work done is equals to Cp, that is specific heat at constant pressure, multiplied by T02 minus T01. If you can recall this from the earlier work done that I have shown you earlier in the lecture from here. And now for the polytropic efficiency, let us draw a curve first. We'll draw the temperature entropy curve, that is T and S. Let us have these lines, which are lines of constant pressure. We will denote each of these lines as P01 and the final line as P02, and this is an intermediate pressure. We can say denote as POL, anything. So this will be, as you guys can see here, we'll have one more thing. This will be the temperature, that is T, and S. Let us have this lines, which are lines of constant pressure. We will denote each of these lines as P01 and the final line as P02, and the final line as P02. So this will be, as you guys can see here, we'll have one more thing. This will be, as you guys can see here, we'll have These are the lines of constant temperatures, and if we give connect this, we get the points 1 and 2. And usually the lines from point, from this pressure and temperature to here, it is usually moving in this dotted process that is known as the actual 2 and 2 dash, well 2 prime we can say. And for each stages, how we are going to define the temperature increment, you can take for any stage like 1 or 2, any stage of it, and mark it like this. I'm not going to congest the diagram here, so I'm referring this as here, which we can refer as dt stage. Sorry, this stage. And if you take in the actual stage, that is like this is the actual stage, and if you take in with this stages, you can just refer it like this, which we will state as dto dash stage. So these diagrams for the polytropic efficiency, I'm sure you have gone, you have come across in your subjects for thermodynamics and thermodynamic subjects in case of thermodynamic processes with the polytropic and adiabatic processes. So this diagram shouldn't be new to you. So once we know this work done is equals to this, we can manipulate it, the work done formula, by writing W CP multiplied by we can just write this work done for the polytropic formula. And just for reminding you guys, I hope you guys have gone through the gas laws and everything from your elementary school, because we will be using one of the formulas here for the adiabatic process, that is adiabatic, or you can say the polytropic process, that is this formula for the points 0 1. This is 0 1, and for the 2 dash, sorry, 2 prime, we get this formula. So I'm just going to write it with the ratio of the specific heats, but since it's a polytropic process, we'll change it in due course to the required formula we need. So work done is equals to, if we introduce the efficiency factor here, the efficiency, then we can write Cp, isentropic efficiency, multiplied by temperature at the 0 2 prime point by temperature at 0 1 minus 1. And we can further write it down as this. We get this formula for the polytropic efficiency in terms of the work done. So from here, obviously, if the polytropic efficiency is given, you guys can just put the value here, and we can get the work done. But if you need the work done, and the work done is given, and you need to find the polytropic efficiency, you can put the work done amount of work done here, and we get the polytropic efficiency value. So this is so this is the basic for you guys should be knowing for the axial flow compressors and everything. Now we can move on to the centrifugal compressors. So just give me a minute. Now, as stated in the, we'll just move on to centrifugal. Now, as stated in when I was starting with the lecture, I already told you guys that centrifugal compressors are preferred where simplicity, lightweight, and robustness are more important than maximum efficiency, along with of course, with a smaller diameter. So these are the cases when we go for a centrifugal compressor. So for a centrifugal compressor, we can have an adiabatic process or an isentropic process, along with the isentropic efficiency and everything. We have this. We still have the same things. So before we begin with that, I'll just put down the steady flow energy equation that you guys already know. Q plus U1 plus P1 V1 plus C1 square by upon 2 is equals to U2 plus P2 V2 plus C2 square by upon 2 plus work done. Now, we have already assumed that we'll be dealing with 1 kg of 1 kg mass of air. So every term here remains, depending upon the process, it remains, but we won't be taking into consideration the amount of heat and the work done, for which I'll come to that point later. But if we consider a horizontal passage of varying area, like suppose continuously crossed, increasing area through which the air is flowing, external heat and work transfer to the, we can assume that there is no external heat and work transfer to the system here. So if we leave those two terms out, we get a generalized equation, a part of a equation from the steady flow equation, which will be involving the internal energy at the inlet and the outlet, the pressure multiplied by volume at inlet and outlet, and we get the kinetic energy at the inlet and the outlet. So if we denote it as 1, and this is at the same datum level, so we do not go with the potential term of the centrifugal forces. Potential term in the steady flow energy equation. Now, let us, for the centrifugal, there isn't, first of all, there isn't much, of a difference between a centrifugal compressor and an axial compressor, except for the fact that, in axial compression, the air is entering the machinery in axial, whereas in centrifugal compressor, it can go in a radial way also. So that is one of the major differences. Otherwise, it is, almost the same. So let me just draw the centrifugal schematic diagram of a centrifugal compressor, and I'll give you a brief description of it. So it is a little bit small here, guys. So the velocity triangle that I'll be drawing for this part, that is 1. I'm drawing it here exactly like this with the vane here. So the air is entering at this absolute velocity c1, and the blade and the vane, that is this vane here, it is moving in this direction. So obviously the blade velocity would be cbl1 here, and if we connect this two, we get the relative velocity, that is cr1, with the inlet angle and the inclination same as in the axial flow compressors. We get this value. Now, yeah, and we also will be seeing that there is no velocity component, flow component here, because it is entering in the centrifugal compressor in the radial way. So the absolute velocity is equals to the flow velocity component, and we do not get a whirl component here, as in CW. Now, for the outlet of the centrifugal compressor, let us draw, since it is going in this direction and it's like this, so the velocity will be coming out in this way, that is C2. The blades will be moving in this direction like this, so we get CBL2, and joining the triangle we get the relative velocity at the outlet, that is here. Now, as usual, the outlet velocity triangle alpha 2, and we get the beta 2, and we get a flow component, that is CF2. Now, as stated in the axial flow compressors that I told you guys, that we get a wall component for the absolute velocity also, and as a result of the relative velocity also. So this will be this arrow here, this will be the absolute wall component from the absolute velocity, that is CW2, and this portion of the triangle we get an velocity component, which is CRW2, but we won't be needing this that much. Just for the sake, I'm just telling you that we get a whirl component from the relative velocity components also. Now, we have done the inlet and the outlet triangle. If you draw a bigger circle and everything, you can just accommodate both of it here. But since the area is too small, so I just drew it separately. Now, how does a centrifugal compressor works? Before that, we need to know the parts of a centrifugal compressor. That is the radially curved vanes, an impeller here, the radially curved vanes, the impeller. We get a casing, and we get a diffuser that is housed in the radial portion of this casing, that is like this, because these veins are like the veins are coming like this. So as the fluid or the air is moving from the inlet to the outlet, it's kind of a diffusing passage from the inlet to the outlet, with subsequent veins placed around the impeller, so we get a diffusing passage. Now, how it works is, air enters the eye of the impeller, that is this, at a mean radius, say suppose rm, with a low velocity, and c1 uh, at the atmospheric pressure, that is p1. Now, depending upon the centrifugal action of the impeller, the air moves radially outwards and radially outwards. So the air is moving in this way, that I already stated, that radial direction, because you don't get a whirl component here, and the flow velocity is equals to the absolute velocity. And during its movement is guided by the impeller vanes, that is the inlet vanes, you can say, impeller vanes. The impeller transfers the energy of the drive that is already driving the impeller to the air, causing a rise in both static pressure and temperature, and increase in velocity. As now, uh, with the increase in pressure and temperature and velocity and everything, and not to forget the angles that we have already drawn here. So just take into consideration that. So the work done would be work done on the compressor, the work input should be equal to the rise in the total temperature, that is point one. Now the second point would be the air now enters the diverging passage called the diffuser, that it is moving like this, the C2 velocity, and there is another curve, if you can imagine it, here, then here, then here, then here, like this. So you get, like, let us draw that anyways here. So you get this kind of curve. As you can see, the area, though it's in 2D, but in 3D actually it goes on in a diverging, and in 2D also you can see the area is diverging from here to here. So the air now enters the diverging passage called the diffuser, where it is efficiently slowed down. The kinetic energy is converted into the pressure energy, with the result that there is further rise in static pressure. So in practice, nearly half of the total pressure is achieved in the impeller and remaining half in the diffuser, that is here. So with a single stage centrifugal compressor, we can, it's safe to say that we can uh, achieve a pressure ratio of 4.5:1. It is easily achievable with a single stage, by the way. For higher ratios, if you need, we need a, you can say multiple stage of centrifugal compression. That is, one compressor is there and you can put it in series through intercooling also, though intercooling kind of reduces the amount of work needed from the centrifugal compressor. Now, if we draw a variation of the pressure and the velocity of air as it is passing through the impeller and diffuser, we can have a diagram of that, a schematic graph of it, like this. Let this be P1. Let this be P2, and let this be P3. So as the air is entering the impeller in the radial way, the static pressure increases like this. And now as it is moving from the impeller to the diffuser through the curved vanes, it further increases as the total kinetic energy is converted to pressure energy in the diffuser. So this part is the, you can say, the impeller part, that is rise in pressure rise in impeller would be this pressure rise in impeller, and this will be the pressure rise del P in diffuser. Similarly, if we get, you want to do a quick check on the velocity, we can have this, like say, suppose it is entering with a C1 velocity here. As it is moving from the impeller to the diffuser, from entering the, velocity, radially the air is entering. So as I have stated that it enters with a low velocity, but the work done in the, by the impeller, by the you can say the impeller vanes on the incoming air, it increases the velocity, temperature, and a slight pressure also. So we get this, that is C2. This is the velocity increment LV in the impeller stage, which with I am giving. Now, as the velocity, air is moving from the impeller to the from the inlet to the outlet and through the diffuser, its velocity decreases, because that's why we are getting an increase in the pressure. So its velocity significantly decreases here, maybe to C3, we can term it as, and this is the velocity decreasing with the down arrow in the diffuser stage. So the velocity decrement here, that is C3 and C1, this can be of the same value, or it can be lower, or it can be a little higher than C1 depending on the problem you're solving right now. Okay, but we need to make sure of one thing, that the formation of cavitation is to be avoided. So that you guys don't need to know here, because that is totally out of for the pumps and everything. But yeah, you need to take care of this small little thing. Now we can just simply move on to the the work done by the impeller and the power required by the power required per impeller. We can move on to all with this, and we'll just be using the velocity triangles that we have drawn here. So don't do not follow this thing. Draw individual velocity triangle for this, for the impeller and for the diffuser inlet and outlet. Separate velocity triangles as I have shown you in the axial flow compressor. So that would be much more neat, and for the relations that I'm going to write down, it will be much more easier for you all to know from that a clean diagram, not this congested diagram. So we'll be calculating the work done by impeller, which we also known as Euler's work done, Euler's work. Now there are certain things that while I'm deriving, I'll let you guys know about what are the notations and everything. But just remember that yesterday when we were doing this, we had gone through this concept of work done, elementary concepts of work done and angular momentum, which we are going to use right now for the centrifugal compressor. So let us begin. The work done should be equals to theoretical torque that we get, suppose torque this T, multiplied by the angular velocity omega, right? Now theoretical torque, how do we derive the theoretical torque? Theoretical torque is a product of the whirl velocity multiplied by the radius, that is the inlet or the outlet radius. Now the total torque would be experienced by the incoming air, and while it is outgoing, would be a difference from the outlet and the inlet. So the outlet velocity is whirl velocity CW2, and the outlet radius as we can denote it as R2, and for inlet it will be CW1 and R1. But the funny thing here is we don't have any inlet wall components. So how do we tackle that? We'll be coming to that in just a while. So for general conditions, if we assume that the flow is not entering the centrifugal compressor radially, we'll have a component like C1, we have taken it to be perpendicular, so it's going radially. So if we just draw it like this and just doing with dotted lines, so we get a component of CW1, which will be this one. If we draw a component, angular, and the alpha shifts to alpha 1 here. But that is not our concern right now. So, but in general, we can have that. So we can write here that CW2 R2 minus CW1 R1 multiplied by omega, that is the angular velocity of the blades. Now, if we just simply input this CW1 R1 omega, that is the work done. So if you further include this, we get R2 omega and R1 omega, which are basically the blade tangential blade velocities, that is CBL1 and CBL2. So we can just substitute that. This can be further expressed in terms of enthalpy, that is 02 minus H01, which can be further written as Cp T02 minus T01, because essentially in a compressor there is enthalpy change due to the rise in pressure, because enthalpy as we know it is a summation of the internal product summation of internal energy plus the product of pressure and volume. So we can, since there is a change in pressure and subsequently volume, and also the internal energy of the incoming air as it is coming in, as it is going, we can express the work done in terms of the enthalpies also. So if there is no pre-wall condition, by pre-wall I mean that Cw1 is equals to 0, that we are doing in this diagram radial. So it makes it even more easier for us to calculate the work done, that is Cw2 multiplied by Cbl2, and we can write joules per kg, that is per kg of mass that we have already considered. All right, about that now. Now we get this equation. We can get a simultaneously we can put the values of this, or the relation of this and this in a by using the velocity inlet and outlet velocity triangles, just as we have used for the axial flow compressors. So we can write that down from the inlet and the outlet velocity triangles, something like this. CR1 square is equals to CBL1 square plus C1 square minus 2 CBL1 CW1. These relations are, we get it plainly from these relations, we can get plainly just in simply from the inlet and the outlet velocity triangles. So just follow the outlet and the inlet velocity triangles and you can derive these results. And if you have any problem, you can just let me know in the comment section and I'll post another video for this. CBL2, CW2. Now, inserting the values for CBL2 and CW2 and CBL1, CW1 from the above expressions, and from these two expressions to the portion here, this equation, the master equation that we got, this one. If we insert that values, we can get the Euler's expression for work done. That is C2 square minus C1 square upon 2 plus CR1 square minus CR2 square upon 2 plus CBL2 square minus CBL1 square upon 2. This is the expression for the Euler's work done for any turbo machinery. You can express it as, be it compressors, centrifugal pumps, axial compressor, then axial pumps and everything that is taking in the centrifugal effect and everything. You can just denote it from the Euler's equation, that is Euler's work. The first term, that is C2 square minus C1 square upon 2, shows the increase in the kinetic energy of the working fluid in the impeller that has to be converted to the pressure energy in the diffuser. So the as the air is entering the impeller, this is the amount of This is the amount of kinetic energy that is increasing in the impeller, and this much amount of kinetic energy needs to be converted to the pressure energy because we are dealing with compressors. So we need to increase the pressure, and this conversion comes in at the diffuser stage. The second term that we are dealing with shows the pressure rise in impeller due to the diffusion action, as the relative velocity decreases from the inlet to the outlet. So due to the diffusion, or as the air is passing from the impeller to the diffuser, the relative velocity decreases, and hence we can see a relative velocity. I mean, with the velocity of the incoming air or incoming any fluid with respect to the blade velocity, that is relative velocity, it decreases due to the diffusion action. And finally, we get the third term that shows the pressure rise in the impeller due to the centrifugal action, because the blades the blades, that is CBL2 and CBL1, they are moving, the inlet and the outlet, so they are moving at different velocities because of the radius. There's a difference in radius. This, we get this kind of formula, just simple formula I'm stating, not any in vectorial form. So we know that the blade velocity, that is this, will increase or decrease depending upon the radius. So inlet radius would be lesser than the outlet radius. So there is the centrifugal action as the working fluid enters at a lower diameter and comes out at a higher diameter. So the third term shows the pressure rise due to the centrifugal action. Now, we can say that the kinetic energy imparted to the working fluid and inverted into pressure energy in the impeller is given by CR1 square minus CR2 square upon 2 plus CBL2 square minus CBL1 square on 2 should be equals to the inlet and outlet, the pressure head that we get here. This is basically what I'm stating here, as the first term is the kinetic energy increment of the working fluid as it enters the impeller and as it leaves. So this much amount of kinetic energy needs to be converted to the pressure energy in the diffuser. While the other two terms, that is due to the diffuser action, diffusion action, you can say, in the impeller, pressure rise in the impeller due to the diffusion action, and this is the centrifugal action, rise in pressure, in the centrifugal action. So as these two are represented in velocity heads, so this much amount of pressure, this much amount of kinetic energy should be imparted to the working fluid and inverted into the pressure energy in the impeller. So this amount of kinetic energy that is imparted to the working fluid should be converted into the pressure energy, and we can say that the total pressure rise in pressure head is this. Now, as I have stated earlier, also this is like during the axial compressor, that the velocity that is exiting the diffuser, we can term it as C3 or C4 or whatever it is. So if we can write the diffuser outlet velocity is C4, we can say C2 square minus C4 square upon 2 should be equals to 2 to 4 dP by rho plus del H, that is the diffuser loss. Now, what is this equation? This is equation, that is the difference of the kinetic energy at the impeller outlet and the diffuser outlet introduces the work partly for pressure increase and partly irreversibility inverted into heat due to the loss in the diffuser. So del H, that is the enthalpy loss in the diffuser for irreversibility of the process. So this is the loss. So apart from that, the increase in the kinetic energy, the kinetic energy that was increased at the impeller, and as it is exiting the diffuser with a velocity c4, that much amount of pressure increase should be given by this dp by rho, that is the differential pressure rise and the divided upon the density of the working fluid. So this is the pressure head we should be getting for the diffuser stages. That is the difference in the kinetic energy at the impeller outlet and the diffuser outlet. Now for the power required by the impeller, is simply mass flow rate multiplied by the wall velocity component at impeller outlet multiplied by blade velocity component at the outlet upon 1000, and we get the power rating in kilowatt. So this is the simple thing that we will be getting from here. Now this is all you guys need to know for the basic concepts of the centrifugal air compressor and the axial air compressor. You need to have the fundamental clears, and these are the fundamental things that you guys should be knowing. So that's all for today's session, guys. And if you have any problem, you can just let me know in the comment section. Thank you.